In this video, I'm going to talk about refraction and Snell's law. I'm going to use both rays and wavefronts in order to do it. Please read through the success criteria I plan to cover in this video. Okay, so let's start with what is refraction. You can see my definition there. Refraction is the bending of a wave as it travels from one medium to another. And that's important, so we always have to have, for example, in this case, I've got my light ray coming in, and it's going to go from glass to air. And it's at the boundary here where I see that it's bending. In this case, do you see how if it had been going straight on through with no bending at all, it would have gone in this direction? But it didn't. It bent away from the normal. Now I can also do this with wavefronts. So if you remember, what this is doing is, let's imagine we're at the beach and we're looking at a series of waves, and this entire row here would be a whole line of crests or peaks. And here would be another line of peaks, meaning that from here to here is one wavelength. Now, as these waves are coming towards the boundary, we can see that we have a change in direction. Now, in this case, if it had have gone straight forward, it would have been here. The normal, which is always perpendicular to the surface, would be here. And now, in this case, my wavefront has bent towards the normal. Now later in the video I'll explain why in one case it bent towards the normal and the other case bent away from the normal. But it's not because I'm showing you the difference between rays and wavefronts. It has to do with glass to air, and in this case air to glass. So let's go into a little bit more detail about why it occurs. And I find this easier to think about if I use our wavefronts. So here's our series of crests coming towards our boundary. And you can see here, when I get to glass, we don't have it moving at a constant speed anymore. In fact, every time I get to the boundary, you can see now this wave, half of it is going a new direction, and this half in air is still going forward until we get to this other medium. Now, we said last time this was bending towards the normal. What really has happened? Well, I like to think of this as this got stuck in the mud. So as my wavefront went forward, this one seems to be lagging behind. Do you see how if it had continued like everything else, it would have been here? And it's not. That means in this medium, the wave must be moving slower. And as we keep going, this side is going to be moving faster. As a net result, my whole wave is going to change direction, because eventually all of this wave will then travel into the glass. One more thing I want to point out. Remember I said that this is the wavelength. The wavelength here is now shorter in my new medium. I'm just using subscripts A for air and G for glass. As my wave went from air to glass, the only thing that's changing is how fast one particle can pass on the energy to the particle beside it. Remember, waves pass on energy, they are not moving through the medium. So the energy is passed on slower. It's a property of the medium, not the wave. But the actual disturbance causing my wave doesn't change. So my frequency, which is the disturbance in my medium, does not change from one medium to another. This is a very key point that you have to keep in mind. Please read my bullet points to make sure you understand all of these pieces. So if I want to measure how much bending is occurring, if I want to measure refraction, a lot of the time we use a semicircular block. And so I've just shown it here with a protractor, but pretend underneath my block I have a piece of glass. I'm going to shine a light ray, because remember, light's a wave, And in this case, I find it easier to explain using light as a ray rather than using wavefronts. So we'll shine the light, a single ray down towards the center here, and as it leaves, because this is from glass to air, I can see here that it would bend away from the normal. So I'm going to change my angle of incidence from 0, always measuring from the normal. And I'm going to go from 0, 10, 20, all the way up to 80 degrees. And every single time I'm going to measure the angle of refraction, that's from here to here, from the normal. And then I've got that I'm going to calculate sine I. So for the first part, sine 0, well, that is just 0. And for sine 10, making sure my calculator is in degrees, that's going to give me 0.174. So what I have here is some sample data from an experiment. Now, if I was doing this for my lab report, I would make sure these all have the same number of decimal places so that I'm showing that all were calculated to the same precision, just like over here. When I do graph it, this is my results. Now you can see I do have some random error because some points are a little bit above or a little bit below, but I think everybody can agree that that is definitely a straight line. I have sine I here, and I have sine R here. So what is that telling us? Well, it's telling us that there is a linear relationship between sine I and sine R, and my gradient for my line of best fit was 1.526. Remember, in physics, we want to take this from the gradient of a graph rather than individual points, because each point has some error. So this would give me a better, more like a weighted average of all of the results. Now this value here is a really important number. It's called the index of refraction, or sometimes people call it the refractive index. It really doesn't matter. Well, what does it mean? It actually is calculated like this. N is c over v, with c being the speed of light in a vacuum. And this is the speed of light in our medium. Now, remember, the speed of light in the vacuum is the fastest thing there is. So, down here, this value always has to be less than c. So what? Well, because of that, this value has to be greater than 1. I'm always going to have something smaller on the bottom. N will be greater than or equal to 1. Now we don't have this equation in our data booklet. Well, many people would say indirectly we do, and I'll come back to that. I like to point out where N can be calculated from. We're going to use it in an equation next. And that would be Snell's law. This is one of those equations that's so important that we actually call it by name. In our equation, we had N1 being air, and remember, if its value is 1, that's because the speed of light in air is so close to the speed of light in a vacuum that this value is basically 1. They will expect you to know that. And 2 would be the index of refraction in the glass, the second medium. Now we have 1s and 2s here because that's what's in our data booklet. I could have wrote air and glass and glass. As long as you're consistent, it won't matter. Notice I also have here the speed of the wave in the medium. So from our experiment, we had N of air, N of glass would be sine 2, which was our refracted one. I'm going to use R just because that's what we calculated, and sine of the angle of incidence. Now if you remember, our graph had sine I over sine R. Let me rearrange that. Our value for air is 1. If I just rearrange this, I'm going to have N of glass going to be sine theta I over sine theta R. Remember, air is 1, so I could just divide by 1 here, or I could ignore it. And what do I have this for? Well, that's the gradient of this line of best fit. I want to talk about a very special case. Now, when I go from glass to air, because I'm going from something with a higher index of refraction, for example 1.5, to something that's lower, air is at 1, I'm going to bend away from the normal. Now, that's going to be true up to a special point. At this special angle, my angle of refraction is going to be 90 degrees. We're going to call this the critical angle. Anything that has an angle of incidence greater than this, it's not possible for us to bend any farther away from the normal. So if I had an angle such as this, I cannot possibly bend any farther away. And what I will get will be something like this. What I have here is in the same medium. So this is not refraction. Remember, refraction was the bending of the ray as I go from one medium to another. This is in the same medium. So this is not refraction, it is actually reflection. And you know from before, the angle of incidence will equal the angle of reflection. So for any angle that is beyond the critical angle, I will only have reflection, and it's in the same medium, so we call it total internal reflection. Sometimes people can get lazy and just write TIR. So let's go through some examples. It says light here is incident on a face of a glass block, and we have an angle of incidence of 40. Let me just draw that in. Remember, I need to have a normal. If the light is incident on the glass block, it's going from air to glass. I'm going to write down my values here. N equals 1, N equals 1.46. And since it's going from a lower index of refraction to a higher index of refraction, I know it will bend towards the normal. This is 40 degrees. I don't know what this one is, but since it's bent towards the normal, my answer cannot be C or D. I've now given myself a 50-50 chance. So let's use Snell's law. And I'll put in the numbers I know. And let me rearrange this. I'm going to put sine 40 over the top here and just write left to right. Sine theta 2 will be sine 40 over 1.46. And now we don't want the answer of sine theta, we want just theta. So I'm going to have to do the sine inverse. Double check, my calculator needs to be in degrees because I've written here sine 40 degrees. And I'm going to pick up my calculator and I get 26 degrees. So the answer is A. We have a ray of light consisting of red and blue light hitting a boundary between air and water. Let me just do a quick little diagram here then. So I've got my red light and my blue light together. I've just drawn them separately. It says here that red light has a wavelength of 700 nanometers. Remember, in your data booklet, you can find that as times 10 to the power minus 9. And they have two different index of refraction. What color will travel light the fastest in water? Well, if we look at Snell's law, the first part says N1 over N2, and the last part has V1 over V2. So whichever one has the highest index of refraction is also going to have the highest velocity. Remember I said they don't have this equation, N equals C over V? Well, they're actually putting that together for both cases. Speed of light cancels out to get this part of the equation. You can also see here that the smaller the velocity, the greater the index of refraction. They're inverses. So in this case, I need to go look. The greater index of refraction will travel the slower speed, or the lower index of refraction will travel at the higher speed. So my answer is red because it has a lower index of refraction. And now B. If the angle of incidence of the light is 30 degrees, which color bends more and by how much? Well, when we look at Snell's law and what we talked about before I do any calculations, I know that blue will bend more because it has a higher index of refraction. The second part of this question says which bends more and by how much. So let's go and use Snell's law to do our calculations. So n1 over n2 equals sine theta 2 over sine theta 1. For red, and I get the value of 22.1. If I do the same calculation for blue, I get 21.9 degrees. Now you might say, oh, but wait, you said blue will bend more and its number is smaller. Well, remember they started at 30 degrees. So this one has bent just under 8 degrees and this one has bent more than 8 degrees. So that's not a conflict of what I said before. The change in theta between the two is going to be 0.02 degrees. Now that might not seem like a lot, and it's true, and so we don't really see this difference when light travels from air to water at a flat surface. The same thing happens in glass. We don't see rainbows through glass normally, but if I have a prism, because of the angle of the two edges are not parallel to each other, it will exaggerate this difference, and that's why you use a prism to separate light into its spectrum or a rainbow. So I have a periscope here. Here's my eye. I'm looking at something over top of this wall, and it doesn't have a mirror inside, but actually has two triangular prisms. Now it's telling me that I'm going to be able to use this. So why would there be no refraction at this boundary? It must be from glass to air. Remember, it would be bending away from the normal. And I only have reflection, then I must be greater than the critical angle, and I have total internal reflection. It tells us the light ray hits the second source at 45 degrees and says draw it until it reaches our eye. So it must be going here, 45 degrees. Now that means to my normal. This is 45 degrees and it's going to reflect at 45 degrees. Till I get to here, I'm going to have the same thing happening. Notice that 45 degrees now will go to my eye. The same process is also used like on the reflectors on your bike. They don't have a light of their own, but when the light from the headlight of a car comes, it's set so that it will bounce, and this is reverted, so it would be bouncing back towards the car. Without calculation, what can you say about the critical angle? Well, we know that this is 45. We've already said then if this is total internal reflection, 45 must be greater than the critical angle. I don't know without calculation what the critical angle is. All I know is it must be less than 45 degrees. Sometimes we'll get these kind of parts of a question on the exam, and they're trying to help make sure that you get the right answer later. Did you get these things the right way around? Do you understand what you should be getting for an answer? Now, given that the index of refraction is 1.52, that degree sign should not be there. What is the critical angle of the glass? So let's go back to Snell's law. Now, since this is a critical angle, we know that sine theta 2 is going to be 90 degrees. So sine 90 degrees. And our incident angle is actually going to be the critical angle. In order for us to have this it would be going from glass, 1.52 we're told, to air. I need to rearrange my equation. And if I pick up my calculator, I get 41.1 degrees. So take a moment and look through the success criteria one more time. I hope you can say yes to all these points.